So in 2019, Google's quantum computer completed a calculation in under 4 minutes. Now that same task would have taken the world's current most powerful computer 10,000 years to achieve. Quantum computing in 2022 is gathering momentum, and while the practical applications are still very scarce, the quantum future is set to break the current cybersecurity infrastructure. Or will it reinvent it? Maybe we should see what all this quantum stuff is all about.
Cybernews explained.
Hey, welcome to Cybernews. Now, while we get all things quantum figured out today, maybe you should just go ahead and subscribe and become a part of our nearly 60,000 community members. It also helps us deliver even more great content. Okay, so modern quantum mechanics can be traced back to 1905. You know, Einstein's theories about light and quantum particles, remember those? Now, the term quantum mechanics took about 20 more years to emerge. Slowly but surely, all the theories and speculation paved the way for new technology. And today, the quantum race is going on. Companies like Google and IBM are pushing advancements, each bragging of having the fastest quantum computer 2022. There are roadmaps of the quantum future with faster and more powerful computers being developed every day. What seemed questionable to Einstein over 100 years ago is now our new reality. But what are quantum computers? Is it really the next evolutionary step in computer technology? Well, not exactly. Truth is, classical and quantum computers are two different things. It's like comparing a bike to a car. Sure, both are going to get you places, but the technology is very different. Classical versus quantum computing are even more distinct. If you take a regular computer and pick the technology apart to the very base, well, you'll just run into ones and zeros, right? The binary system. Every operation, every single calculation boils down to the same two numbers, and the results will always have the same two outcomes. Quantum computing, however, uses quantum bits, or in short, qubits. The operations happen on a way smaller scale. While the qubits can also represent either a 1 or a 0, they have a strange property, a third state, called superposition. So let's break that down. Okay, imagine a qubit as a clock pendulum, swinging to two sides. Left side is 0 and the right side is 1. Now, the pendulum won't stay long at any position for a long time. It'll constantly swing in between, bouncing from one side to another. In a similar way, the qubits exist on a scale from 0 to 1, being able to take position on it, but never ever staying still. While the swinging of a clock pendulum is slow and soothing, the qubit changing the states is violent, spinning in all directions at once all the time. That's exactly why quantum computers are faster. The speeds at which the particles move provide the means to run an immeasurable amount of processes in an incredibly short amount of time. And of course, there are more differences between a classic computer and a quantum computer, like the fact quantum computers need near zero temperatures to operate properly, or that they're based on software. The technology is complicated, but it's necessary to accommodate the incredibly fast problem solving that it can do. Because of the qubit speeds and superposition, quantum computers can take certain problems and solve them in a super short amount of time, like the Google quantum computer demonstrated in 2019. But these capabilities bring some downsides too, and this is exactly where the dangers of quantum computing start to emerge. Okay, see this doomsday clock? Now, according to CSA, once this countdown runs out, quantum computers are set to break the cybersecurity infrastructure, at least the ones we know today. So here's why quantum computing is actually so dangerous, at least in theory. Quantum computers will be able to break 2048-bit RSA encryption in just under 8 hours. Yep, a classical supercomputer would tackle the same task for, just about 300 trillion years. And so the quantum arms race has begun. Russia, India, Japan, the European Union, and Australia, all carrying out significant quantum research. It's almost a modern-day space race. The US and China quantum computer development efforts are advancing the fastest. Both parties are chasing after the prize of cracking their opponents' records and state secrets. So whoever has the most processing power will secure an advantage over their rivals. At least that's the idea, right? But where quantum technology poses a challenge, it also creates a solution, and that's quantum cryptography. It applies the principle of quantum mechanics to not break encryption, but rather to create it. The biggest advantage is that you don't need a quantum computer to make a quantum cryptography system. It uses photonic technology to transmit data from one point to another. The technology itself is fairly complicated, but it boils down to one specific advantage. Any potential eavesdroppers can't read, forward, or copy the information without altering the state of the photon that carries it. If they try, the whole thing just goes to shambles. Quantum cryptography comes with the promise of being unbreakable. Now, whether such claims are actually possible is still a question to be answered. But there is one definite certainty. It's the future of encryption. If quantum computing creates a problem and quantum cryptography solves it, what's the point, right? We're right back where we started. Well, not everything is actually so black and white. Quantum computer applications can have a much more positive impact. This technology could transform underwater navigation, help monitor the movement of data. By deepening our understanding of particle behaviors, it could also pave the way for significant improvements in medicine. And then there are practical applications that may look like they've been pulled straight out of a future sci-fi film. Yeah, teleportation. Okay, so how is quantum teleportation possible? Well, this technology is not for human teleportation, at least not yet, because that would be gross and creepy. It works on a much smaller scale, with the main application being the transportation of data. Quantum transportation relies on another property of the qubits called quantum entanglement. Turns out two particles can link up across space and time, and if one changes, the other does too. For now, according to NATO, the greatest distance over which quantum teleportation has been achieved is 50 kilometers. Future quantum computing will tackle the challenges of scaling these processes with one main purpose in mind: secure communication over large distances. Okay, now some of this stuff might be far away, but if these technologies start emerging, well, guess what? We're going to be the first to cover them. So yeah, you might want to like and subscribe to our channel. That way you're not going to miss a dang thing. So whatever wonders the quantum future holds for us, one thing is certain: the current approaches to quantum computing are paving the way for huge technological improvements. That's exciting. Hey, thanks for sticking around until the very end of Quantum Computing Explained video. If you're starting to grasp how quantum computing works, great. If not, well, here's a reassuring quote from Nobel Prize winner Richard Feynman: "If you think you understand quantum mechanics, you don't understand quantum mechanics." Yeah, that would be me. Okay, see you in the next one.